All right, we're going to finish up chapter 3 today. We're going to talk all about series. And then the chapter 3 test will be next class. We'll wrap up chapter 3 before break and let you guys start up fresh and return. So, for example, consider the geometric sequence 1, 1/2, 1/4, 1/8, etc. How do I know that's a geometric sequence? This first guy up here. How do I know that's geometric? Good, because there's a constant common ratio of 1/2. If I look at the next term, I can get it from the previous term by multiplying by 1/2. Okay? So notice there's commas in a sequence. If I trade out those commas for plus signs, that's now a series. If the series has a dot, dot, dot at the end, we call it an infinite series. If the series doesn't have a dot, dot, dot at the end, we call it a partial sum because it's only part of the sum for the entire series. So notice I use the notation S for series. So we have S sub 5 is the 5th partial sum. So it's the sum of the first 5 terms. You guys okay with that? So as you imagine, if I have the 100th partial sum, that's going to be pretty obnoxious to write down. I don't want to have to do that by hand, so I want to invent like a new notation to kind of represent those sums. That new notation is called a summation notation or sigma notation. So we can use that capital Greek letter sigma here. We use the bottom, we declare a index variable, so that's the letter I. And then the start of my sum is using the first term. And I'll add up until the 5th term. That's the end, that's my upper bound. And the things I'm adding up are the sequence AIs. So I'm adding A1 plus A2 plus A3 plus A4 plus A5. That's the terms of the sequence from 1 to 5. Everybody's okay with the notation there? We've done summation notation in your previous pre-calculus class, so I'm kind of counting on this being familiar. Okay, so let's look at a couple of examples. We're just going to go back and forth between writing things in an expanded form and writing things in summation notation. Okay? So if I look at this first example, if I want to write this in expanded form, what am I going to do? I'm going to plug in the values from 3 to 6 into I, and then add those things up. Everybody okay with that? And then you can type that in your calculator, press enter to get the number, but I'm more interested in making sure we go back and forth from a summation notation to an expanded form and an expanded form to a summation notation. That's typically the part that's harder. You guys are usually pretty good at typing stuff in your calculator, give or take. Everybody feel okay?
Yeah.
Okay. All right. So the next one, we have a expanded form, and I'm going to rewrite that as a summation notation. So I'm going to use I as my index variable. If I look at the terms, or the terms of this series, what does it look like the pattern is going on here? Okay, the exponents are going up. Okay, so how would we write the sequence of terms 3 to the 3rd, 3 to the 4th, 3 to the 5th, 3 to the 6th, 3 to the 7th? So what's changing? The exponent. So that's where the variable should be, right? What is the exponent starting at? 3. What is it ending at? 7. So you could write it that way. Not the way I would intend for you to write it, but that's okay. It's correct. Ideally, you should look at this and go, hey, this is a geometric series that we're adding up. Right? All we're doing is multiplying by 3 each time. So you could have also written this as the sum I equals 1 of the sequence 3 to the third, the first term, times r, the common ratio, to the n minus 1. And then this is the what term in our sequence? 1, 2, 3, 4, 5th term. So I could have also written it that way. That would have been the way I would have intended you to write it, but the first way is fine. It's correct. Nothing wrong with that. One of them we used a little bit of like math sense, and the other we used like the established formulas that we've been using on the quiz. Either is fine. So far, so good. Okay. Our next example says to evaluate the sum from n equals 0 to 5 of 2 to the n. So let's write that out into an expanded form. So it would be the first thing. Adding a bunch of stuff together, right? What's the first thing we'll be adding? So we're using this, and what are we going to be plugging into it? The numbers from 0 to 5. So the first thing is 2 to the 0, and then it's you guys need to wake up this morning. And then again, you could type that in your calculator to get the actual number. That's fine. If you can do the expansion, I trust you can get into your calculator. All right, let's look at the next one. Here it says to evaluate, and woof, a lot of terms are going to be adding up here, right? This is not a problem to do by hand. This will be one that we'll use the calculator to handle for us. And the best way to get the calculator to handle this for us is to get it into a summation notation. So that would be my first step. So first question I'd want to ask is this series arithmetic or geometric? Or neither? Arithmetic, geometric, or neither? You should be able to do this. You just had to do it on the quiz. We just took on Friday or whatever. Okay, well, let's start. If this was arithmetic, my common D should be like 2/3 minus 1/2, right? If I make a common denominator, that's going to be 4/6 minus 3/6, so 1/6. Now if I want to check that, 2/3 plus 1/6 is going to be 4/6 plus 1/6. That's 5/6, which is not 3/4, right? Is it arithmetic? No. Okay, I'm going to erase this. Is that fine? Now let's check if it's geometric. If it's geometric, the R should be 2/3 divided by 1/2, right? I know to divide fractions is easy as pie. We flip the right and multiply. So the R should be 4/3. If that's the case, then 2/3 times 4/3 should equal 3/4. Is that the case? 8/9, is that equal to 3/4? No. Is it geometric? No. Okay, so it's neither, which means that we're going to have to come up with the formula by hand, because we won't be able to use a formula. Or will we? If your sequence is a fraction, oftentimes, if it's neither arithmetic or geometric, maybe I can treat it as the numerator is arithmetic or geometric, and the denominator is a different arithmetic or geometric sequence. So if I do that, if I look at the numerators, 1, 2, 3, 4, all the way up to 99, is that arithmetic or geometric? Arithmetic, great. What is the D? 1. What is the first term? 1. So it's basically just out, right? Okay, if I look at the denominator, is that arithmetic or geometric? 2, 3, 4, 5, etc. Also arithmetic. What's the D? 1. What's the first term? 2. I plug that in, I should get I plus 2. Okay? So we're starting with the first term. What are we ending at? Should be really easy to see. 99. Because I is the term number. That's my last term. So I can do that. So do you feel okay there? Okay. Now, to do this into my calculator, once I've done this, sign in. Oh boy. Sometimes this takes a long time. Oh, not today. Okay. So, what I'm going to do is I'm going to, if you have your graphing calculator and would like to follow along, I encourage you to take that out and do so. If you're just like, yo, I'm just going to sit and watch and chill, that's okay too. You can always go back and find the video around the 13 or 14-minute mark and watch what we do. So the command we're looking for is in the math menu. So I'm going to press the math button. And the command we want is way down towards the bottom. So I'm going to keep scrolling. I want the summation command. And look, they even were nice enough to put that little sigma symbol next to it so we remember what that is. So I'll press enter. And now we're basically going to type this in exactly like it looks like on our sheet of paper, but we can't use the letter I as our index variable in the calculator because I is designated as the imaginary number there. So what do we suppose I'm going to use instead of I? X. You guys are so smart. Oops. Come on. And what if I suppose I wanted that, and not as a decimal, but as a fraction? Oh, come on now. You can surely do this, calculator. No, you're just going to refuse to do it for me today? Fine. I hate you too. So to round it to 3 sig figs, I guess that's 94.8. Is everybody okay with the calculator? Yes. It's always acceptable, unless it asks for specifically for a fraction, in which case I don't think I would do it for a problem where the calculator doesn't want to give you a fraction. Now keep in mind, could I have done that for this one? Sure, right? Could I use that same command to do this one? Sure. Could I, instead of typing this into my calculator, type one of these two in my calculator and press enter? Sure, right? So it depends on the direction. If all we're looking for is the value of the sum, then you can just rewrite it as a sigma notation and then use the calculator to evaluate. That's okay. So far, so good? All right. So a couple of properties about summations. So one is that you can factor out a constant outside of the sum. So for example, the sum of 2i is the same as 2 times the sum of just I. Everybody okay with that idea? And the second property is that I can distribute these summations across addition or subtraction. Which may be helpful if I'm trying to use a formula to do these summations. Now, we have 2 special types of series, just like for 2 special types of sequences. We have arithmetic, geometric. So our formulas for an arithmetic sequence are as follows. If you're choosing to take notes, I'm going to tell a funny story while you're writing this down. So the first summation formula has kind of a funny story attached to it. So famous mathematician Carl Friedrich Gauss, he's back there on the board there, like 1700s, Bavarian. I don't think Germany was a country yet. I don't know if it's Germania or what it, what it would have been, Bavaria, if it's Prussia at that point, I don't know. That whole region in, medieval through Renaissance kind of changed names about 150 times. I can't keep track of what it's been called. But it's like one-room schoolhouse style, right? So Carl Gauss is sitting there in his classroom. He's like the youngest kid in there. Teacher's having a bad day. Just wants to give the kids something to do to keep them busy that kind of everybody can do. And he's like, I want you to add up all the numbers from 1 to 100. And about 30 seconds later, Carl Gauss walks his his little chalk slate up to the desk, and it's 5,050. Done. And the teacher's like, you can't be done. How did you add up? What did you do? He's like, the answer is 5,050. It's done. I did it. I added them. And he's like, where's your work? Because the teacher has no clue what the actual answer is. He doesn't care. He just wanted something that was going to keep everybody busy for a half an hour while he, didn't have anything, And the way that Gauss did it is he made the observation that if I take the first and last term and I add them together, I get 101. If I take the second term and the second to last term, 2 and 99, I add those together, I also get 101. If I take the third to last term and the third term, add them together, 3 and 98, I also get 101. I can do that pairing and get 101 for every pair. There's 50 such pairs in 100, right? I can pair up the numbers in 150, make 50 pairs. So the answer should just be 101 times 50, which is exactly what this formula is saying. It's the first term plus the last term times the number of terms divided by 2. So there you go. Maybe you'll remember the story, the formula, because you remember the story. I don't know. Okay. For a geometric series, we have the following two formulas. Note that for an infinite geometric series, the answer is not infinity, which is like kind of wild to think about. It's cool if you're telling me I can add up infinitely many things, and I can get a finite answer. Whoa, that kind of blows my mind. The idea is that if that R value is between -1 and +1, so for example, like a half, what happens when I multiply a number by a half? Does it get bigger or smaller? Smaller, right? And suppose I multiply a number by a half like infinitely many times. How small is it eventually going to get? Basically, it becomes 0, right? So at some point, like I've added up, I've multiplied by a half enough times to where like each additional term that I add on basically isn't like adding anything at all. It's basically like 0. Now, that doesn't happen for all geometric series, right? If the geometric sequence has an R value that's bigger than 1 or less than -1, I should say bigger than or equal to, then the thing goes blasting off to infinity and there's no hope, right? But if not, that's it. Now, keep in mind, do you really need to use these formulas? Most of the time, you could just use the calculator, right? The calculator has the formula built into it. But there'll be certain types of problems where, you know, like kind of need the formula to be able to solve it. So just kind of keep that in mind. I'm going to buzz through a couple more examples, and then we're going to be donezo's for today. Sound good? Consider the following arithmetic series that contains 50 terms. It starts 3 plus 8 plus 13 plus 18. How do I know that's arithmetic? Good. Each term is increasing by 5. Everybody see that? There's a common difference of 5. Okay. It says write the series using summation notation. So we identified that the common difference is 5. And we know the first term is 3. So my formula for that sequence is going to be 5n minus 2. Everybody feel good there? So if I want to then write this as using summation notation, I can do that. Everybody okay with that? Where did the 50 come from? Why is there a 50 up there? Yeah, it told me in the directions, right? It says the series has 50 terms in it, so 1 to 50, that's what we're adding up. Pretty feel good? Okay. It says find the partial sum for the first 50 terms of the series. So let's do this without the calculator, just to get you a feel for using the formula. So using my formula for an arithmetic series, that's the formula, right? With the things plugged in 50 plugged in for n. So we know a sub 1, we know that's 3. What's a sub 50? How am I going to get that? I'm not told what that is. But I have the formula for the sequence, right? Because I have the explicit formula. I can just plug 50 in, and there's my answer, right? So 248. So I'm going to just do 3 plus 248, that's 251 times 20. And again, I probably wouldn't bother doing any of the simplification I just did without my calculator. I just calculator after I filled in the values to the formula because, goodness gracious, why take the risk, right? I got good faith I can get into the calculator, much less faith about my mental math skills. I could probably do 25 times 250. Maybe not. It's hard, especially at 8:16 on a Tuesday. But everybody feel okay? This is basically the gist of it. Let's do another example. Okay. Says consider the sequence in figure 3.8. That's our sequence right there. F1 has 1 squares. How many squares are in F20? So in F1, I have 1 square. How many squares are in F2? And then in 3, and then 4, and then 5. What am I noticing these are? Yeah, they're odd numbers, but yes, so this is an arithmetic sequence where the cognitive difference is 2. The first term is 1. I plugged that into the arithmetic sequence formula, which I did not show, I just did it in my head. Because at this point, I'm trusting you guys can plug stuff into a formula. So there's that. So if I want F20 then, it's 39. Okay. Is there a figure with 149 squares? If yes, which one? If not, why not? Well, what I'm going to do is I'm going to say, okay, 149, or is there like an n where I get 149 out of this, right? So I'm just going to solve for n. So I add the 1 over, I get 150, and divide by 2. 149 is the 75th term in that sequence. So I could write like F75 is equal to 149. Everybody okay with that? Now you could count that off too if you wanted to be like 1, 3, 5, 7, and just kind of keep track. But like stabbing in the eyeballs, I don't want to have to do that. It sounds like so tediously boring and rather time consuming, and like, you know, I got a lot of better things to do. Part C says find the number of squares in the first 880 figures. So that's going to be F1 plus F2 plus F3 plus F4 all the way up to F88. What are we talking about doing here? That's a series. Nice. I know it's early, but goodness gracious. Okay. basically we're doing that, right? And I know that I have a sequence for fi. That's 2i minus 1. And this point, we could calculator this, or we could use our arithmetic series formula. Either is appropriate. Let's calculator it just to kind of see that one more time. Where do I go to type this into my calculator? What button? Math. Good. Good. And I'll do x for I, so x equals 1 to 880 of 2x minus 1. 744 or 774400. Okay. So far, so good. Now, part D starts talking about the number of line segments. So I'm going to call this like Li then for lines. So the first figure has 4 line segments. So how many are in the second figure? 4, 8, 10 it looks like. And the third figure, 4, 6, 9, 11, 15, I think. Somebody's got to double check me on these. 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whew, let me double check. And then we'll do one more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2. And at this point, who sees the pattern? Arithmetic or geometric? Good. What's the common difference you saw? 6. Again, I shortcutted typing it through the formula, or plugging it to the formula. And I forgot what we're doing with this. How many line segments are in F20? So I need L20 then. And that's easy. I just plug it into my new formula I wrote. Is everybody feeling all right? So far, so good. NBD. Is there a figure with 550 or 450? Which one? And then why or why not? Okay, we'll do it the same way. You know, is there some L that has 450? Well, heck, I don't know. But if there is, this has to work. Now, if I take 452 and divide that by 6, that ain't going to work. Who can do the mental math in their head to tell me why that's not going to work? 6 is divisible by 2 and 3, right? Is this divisible by 2? Absolutely, because it's an even number. Is it divisible by 3? No, why not? Because the sum of the digits, 4, 5, and 2, that's 11. 11 is not divisible by 3, so 452 will not be divisible by 3. So we'd say no, because n equals 452 over 6 is not a natural number. care what the decimal actually is. I just care that it's a decimal and not a whole number. Everybody feel good? So far, so good? Okay, and then F. Find the number of segments in the first 880 figures. Well, that's piece of cake, right? It's basically the exact same setup as the last one, except I'm using L. So I have a different formula for L. And we'll do the calculator again, I guess. Boop, boop. 23, 24, 080. How's that feel for you guys? Okay, I'm stopping here. You guys have about 30 minutes left in class. You should open up your book to the chapter 3 review problems and start working on those. I would strongly advise trying to complete that chapter 3 review before the test date, which would be next class, as I think that would be an excellent preparation for the test that I'm going to give you. So you should be taking out your tablets and loading up that online or that PDF of the book and actually doing some of the problems from the chapter 3 review instead of just copying them out of the back of the book. You know, not that anybody's doing that. Your all lack of eye contact tells me that you're definitely doing that. This time, do some of them. Okay? Especially if you don't know how to do it. Any questions for me? I think if we look at the test description page, you should be able to, when given a sequence of consecutive terms, identify whether it's arithmetic, geometric, or neither. That's a repeat from the quiz, and a lot of us got those things wrong. I would make sure that you feel real good about that. Use an arithmetic sequence to do currency exchange problems. You had very little problem with that on the quiz. I would expect that to continue. From the given information, find the nth term of a sequence, arithmetic or geometric, and then compute the value of the specified term. Remember that you can do that on the calculator, right? Find the value of the sum of the first however many terms of a sequence when it's arithmetic or geometric. So again, if you're using those formulas I presented to you, or you could use your calculator. My suggestion to you is I would fill the stuff into the formula and then use the calculator to do it. And that way you have a little bit of work shown for some partial creds in case you do something silly. Use geometric sequence to do finance-related story problems. By that I mean like compound interest kind of stuff. And then convert a series into sigma notation and then to expanded form. So you should be able to go back and forth from the sigma notation to expanded form or expanded form back to sigma notation. And we did several examples of that in the notes today, so that should be relatively okay. The trickiest one is when you get a fraction that's neither. But again, the trick is to just look at the numerators and denominators separately, and they should both be either an arithmetic or geometric sequence. Definitely different sequences, but okie dokes.
Yes.
Okay. I'm going to stop the recording and let you guys get to work.